From the first steps of India's lunar journey to the historic soft landing of Chandrayaan-3 near the moon's south pole, India's exploration of the moon has been a story of remarkable technological ambition, perseverance, and teamwork. Today, we are honored to welcome Shri M. Sankaran, sir, distinguished scientist and director of R Rao Satellite Centre, ISRO, the center responsible for the design and realization of Chandrayaan-3 spacecraft. So we welcome our sir for to this podcast and initiating this podcast. Firstly, we want to know the person behind the scientist, the person who has learned science and developed the interest in space science, how your journey has initiated, sir, how you developed the interest in from your childhood to your young age to your adulthood, how you maintained this interest throughout your life.
Okay, thank you, Devansh and Aman. To start with, I should admit that when I was a child or going to school, I was not really knowing anything about space or science. What is taught in schools, I studied in all village government or municipal schools throughout my entire career. So there you are taught only what is in the syllabus book. So there is nothing, I would say that I was inspired in when I was in first standard or 10th standard. I cannot tell. I can tell that like any other student, I was learning what was taught to me. While I was in college, when I was doing my bachelor's and master's, that is a time when the whole of this country, India, people getting employed in banks was becoming very popular. Writing examination, probationary officers examination for banks and getting employed in banks with a good salary was everybody's dream. At that time, my only thinking was that I should not go for a job where I'll be doing a clerical work or sitting in a desk and writing things. I should not do that kind of work. I should do some technical work. That was the only requirement I had when I was in college, even during my master's. So that is how my childhood and college days were there. And like it was happening those days in the mid 80s, the ISRO recruitments happen through advertisements in the newspaper, and people see the advertisement, apply, and get selected. So I also applied like that and got selected. But there is a story in my selection and joining also. Maybe some other time I will tell that story. It was very, very lucky break. In fact, after 1 year after attending my interview, I got into this job because my house had shifted, so the appointment letter didn't reach me at all. It took through a very, very long route because of the government procedures. You see, government has some procedures for appointments. When somebody is sent an appointment, if that person doesn't turn out, the government doesn't leave it like that. The government tries to reach out to the person to ensure that that person comes back and join. Because of that procedure, only after almost a year, I came and joined ISRO Satellite Centre, ISAC, today called as the UR Rao Satellite Centre. So till I joined ISRO, my only requirement was to do some technical work. But mid 80s ISRO had so many stalwarts. There were so many people who were your role model the moment you come to know about them. Like we had Professor UR Rao, Professor Satish Dhawan, Dr. Kasturi Rangan. Like that, a large number of people. There are many other less publicly known scientists, leaders were there, who are the inspiration for anybody to learn the work in ISRO. There is, we all call in ISRO something called as the ISRO culture. Yes. How we work in ISRO. So this ISRO culture is from all these leaders and these stalwarts who had started this work in the late 60s and early 70s. So we had so many people to look up to and learn from. And when you start learning from them and inculcate this habit, which is now being called as ISRO culture, you have nothing else to do. You have to do your work as sincerely and as completely as possible.
Yes. So while we were before this podcast, we got the opportunity to interact with Shri S. Kiran Kumar sir, and we asked the same question with him. And whenever we talk to such personalities like you and Kiran sir, there is something that they tell us that they didn't had some kind of peer pressure and they followed their passion during their childhood. Like I recall that he was mentioning of making a projector from scratch. in his childhood. So, which was a far beyond more technology during that era. So, is there some story behind you that you were also quite passionate in doing some sciences or engineering during childhood? Or can you tell about that, whether you were having the peer pressure of following the engineering or like we have today, or it was your passion or interest which was driving you towards this field?
See, when I completed my +2,
Yes.
that time, my home state, Tamil Nadu, there were only some 4 or 5 engineering colleges, entire state. Maybe probably about 500 seats, 1,000 seats maximum were there for engineering. So getting into engineering was not an easy job, particularly for people coming from lower middle class. Getting into engineering is very, very, very difficult. So I never had the thought that I should go to engineering. When I completed my +2, I knew that I want to go into science. So I chose BSc physics, maths, and chemistry. So maths and chemistry as minor subjects and physics as the major subject. That's how I got into physics. I never even imagined that I should get into engineering because I know that my family cannot afford it. So that is those days were like that. Regarding the any pet projects or any these things and all, those days everybody used to, all students, as far as I know, try to make one radio. Everybody will want to make one their own handmade radio. We ourselves will fabricate a radio to receive the all India radio signals. Initially, shortwave signals we used to pick up. Then FM came, then FM radio. So I would say that when I was student, at least in the +2 and bachelor's time, this is the only passion we had, to make a radio, receive. You want to receive BBC shortwave. You used to get BBC signals, and also Ceylon radio signals we used to get. So we want to make one radio and receive these signals. That used to be the passion for me at that time. But all this went off the moment we get into PG. The PG work time, the studies were more intense. You need to study more seriously. So all other side activities all went off. Concentrate only on the studies during PG. That's how it was.
You have spent nearly 4 decades designing satellites. What do you see Chandrayaan-3 resting on the moon today? What emotions do you personally feel, sir?
I should tell that it is not the same or a single emotion. I would say from the time it touched down till today, I have different emotions in different times. The first one, as soon as it touched down, the immediate reaction or emotion was relief. That it is over, it is successfully done. It is a big pressure of the head. So the first emotion I had after the successful landing, was relief that we have done it. We don't need to struggle now. This is the first emotion, and of course it is followed by happiness, joy, because obviously it is something to rejoice. So that is next few hours, few days, it was joy that you are celebrating with all your friends and colleagues who made it possible. And subsequently, the emotion which took over me was pride in my team. The team is what has made this feasible. That is what has made the whole country rejoice. So I was so proud of my team. Then this pride changed to gratefulness, because that is what you realize, that this kind of success is possible only because of the dedicated and selfless efforts of so many hundreds of people. I should say it should be in thousands of people have contributed to make this happen. So, and also the kind of response the entire country gave for this achievement, you always feel grateful, and you feel humbled and grateful. So that is the final state I came to, that you became grateful and humble. And after this is over, now it is 3 years since this has happened. Yes. The feeling now I have is more of responsibility. That is what I feel most of the senior people in the organization of ISRO, we have now a feeling of responsibility. Now that we have done this, now that we have got so much affection from the people of this country, now we should be even more responsible, and we cannot allow any reduction in our commitment and dedication. So that became the final. Today I have only this emotion of being responsible, that we have to do even better. We have to do whatever is needed to keep the country proud.
Yes. That was a huge moment when the Chandrayaan-3 landed over the moon. And so, with the ISRO, the Indian population and specifically someone who was interested in the space and enthusiastic about the space, like me and him, we were also evolving. As the mission Mangalyaan got succeeded, Chandrayaan-1 got succeeded, and Chandrayaan-2 with a small amount of failure. But again, then come back with the Chandrayaan-3. We have seen the ISRO developing and becoming more stronger. So, sir, can you tell the stories of these three missions of Chandrayaan-1, Chandrayaan-2, and Chandrayaan-3, that how ISRO evolved, how it learned from its failures or its outcomes or shortcomings, and what improved at the next stage, and finally the historic mission of Chandrayaan-3? Can you tell this about in a brief story?
I would believe that the story of the three Chandrayans is more or less similar to the story of modern India.
Yes.
Okay, when India became independent, we were really very weak country economically. The country had famines, that is food shortage, at regular interval. The country was finding it difficult to feed its own people, and it was getting as gift wheat from foreign countries and feeding its people. So the priority of of India in the 50s, 60s, 70s, 80s, and all was to feed its people, to make the people have at least 2 times the food. Then came a time when India thought that it should revive its economy and get into new way of doing business and make its economy grow. And today, India is a leading nation of this the world, where we are today. We are the fourth largest economy in the world, one of the leading spacefaring nation, and world's number 2 military power. Like that, India has emerged in various sectors towards the top. The Chandrayaan story is also like that. Till the turn of the 20th century to come into the 21st century, the ISRO's activities were mainly concentrated on what was originally given as a vision by Professor Vikram Sarabhai. That is to make the space technology to serve the public of this country, the people of this country. That is to develop the necessary infrastructure, communication, or Earth observation. Earth observation is mainly to help the government to do the governance. That is to ensure that the food production is good, monitor the food production, how the rain and surface water in the rivers, how they are being managed. Like this, a number of governance related activities only the ISRO was doing till of the late 90s. And that is the time when the Kargil war happened. And also India was emerging as an economic powerhouse after the liberalization and the new economic policy of the 90s by the government. This is also the time, the Kargil war and this economic liberalization. These were the two things which also made the leadership in ISRO also to think in other thing, that we should develop certain capabilities in space which will not allow problems like the Kargil war to repeat easily. This is one. That is where India started developing strategic Earth observation capabilities, communication capabilities. After that only, the outcome of that is what we have today. We have seen the outcome of the Indian satellites' performance help during the Operation Sindoor. That time also India decided that we should also now look at India demonstrating its capability as a space power, not only as using the space technology for the benefit of the people. We should also now show India as a space power. That is when Chandrayaan-1 was conceived. So I would say the Chandrayaan-1 story is India emerging out of its self-imposed restrictions and coming out of its limitations. Chandrayaan-1 was like that, because to make a spacecraft go to moon from Earth and orbit around it without actually crashing on the moon or flying past the moon is like from here throwing a ball and the ball exactly falling into a hole in, say, Varanasi. The problem is that critical, that severe, that if you can imagine, I can throw a ball from Bangalore to Varanasi, and in a, say, 1 foot hole, the ball has to go and land perfectly. That is the kind of precision that was required to reach orbit in the moon. So once India developed this capability and demonstrated in Chandrayaan-1, it gave the confidence to the scientists and engineers and also all policymakers that India is capable of doing these things. That India's story of emerging out of its restrictions is Chandrayaan-1. Chandrayaan-2 is the story of India gaining its confidence and India demonstrating that it dares to dream and imagine. That was Chandrayaan-2. The Chandrayaan-2 conception, originally Chandrayaan-2 was conceived with a lander given by Russia. Only the rover was to be made by India. But because of some problems, Russia backed out. So in the year 2012-13 time frame, it was decided that we ourselves will make the lander. And that is how the Chandrayaan-2 journey started. Now the Chandrayaan-1 discoveries and Chandrayaan-2 near success is also one of the reasons the entire world is now today rushing towards moon. Though the Americans and Russians were repeatedly going to moon in the 1970s, from mid-70s till Chandrayaan-1 went, there were no significant lunar missions anywhere in the world. Everybody has stopped going to moon. So Chandrayaan-2 story is that there is still a reason for humankind to reach moon. That was the story of Chandrayaan-2. And Chandrayaan-3 represents today the resurgent, powerful, economically strong India. This is exactly the story of Chandrayaan-3. That when even today, after Chandrayaan-3 successfully landing, you would have seen a couple of missions around the world try to land on moon near the South Pole and failed. This is landing on moon, particularly near the polar regions, is that difficult. Even for those people who have done it before, who have done it 50 years ago, doing it again is not granted. It cannot be taken as granted. It is that difficult. So India doing it in the first instant and doing it so easily and for everybody to see. It is not that it was the practice of live telecasting lunar landing started with Chandrayaan-2. It was not there before. Nobody did the live broadcasting of a lunar landing before that. We did that. This is what the story of Chandrayaan-3 is about. Chandrayaan-3 is the story of India emerging as a strong economic and military power. This is what the story. Now, scientifically, you see, Chandrayaan-1 has inspired many things because that presence of water molecule in Chandrayaan-1, detection of water molecule in the moon surface or in the moon's very light atmosphere, that has driven many things subsequently. So this story, I would say, is the story of India, modern India. How from self-imposed restrictions, India is emerging today as a very powerful nation. That is how Chandrayaan-1, 2, and 3 are.
Yes. So as you mentioned that Chandrayaan-2 was the first mission which was completely broadcasted on various platforms, and I still remember that it was around after the midnight it was being telecasted as it was around 1 or 2 a.m. in the morning when it was scheduled. So the whole India was awake to see that as various channels were broadcasting that. It was like a very celebrity moment for all the scientists at ISRO. And even that happened with Chandrayaan-3, and we felt that huge amount of respect and gratitude and proud moment for ISRO. And so we remember that there was some coinciding mission with Russia, that Lunar 25, which was not able to succeed. Were there any interaction or communication between ISRO and Russia Roscosmos that you were having during those times? Were you following each other, or just can you tell about that?
No, there was no discussion between our team and the Luna team from Roscosmos about our mission. We know that they are also coming to moon. We had already more than about a month earlier than them, we had launched because we had a smaller rocket. So we had to take a slower route to reach moon. Yes. They have a very powerful rocket, so they could directly come to the moon very fast. So even after starting about a month late, they reached moon earlier than us. No, there were no discussions between the two spacecraft team. But we know that what we are doing, and they know what they are doing.
Could you take us through the journey of lunar spacecraft from the drawing board to the surface of the moon, like from designing it and by the seeing and landing on the moon?
Any satellite design, lunar or any other satellite also, is first you define what you want to achieve with that mission first. What you want to do with that mission. In the case of, say, Chandrayaan-3, the main outcome from that mission was successfully landing on moon and making a rover roll out of the lander. This was the main motive of that mission. Now you also decide now what is the launcher you want to use, what is its capacity, how much mass it can take. Now you decide now out of this mass, how much is required for propellant, fuel, and how much can be reserved for the remaining things. Now the propellant generally for a moon-like mission, if I have to take say 100 kg to moon, you require nearly about 500 kg propellant to take it, make it to reach moon. So that is the kind of scale we are talking about. So if your rocket is able to lift 5,000 kilogram, your satellite, other than the propellant, cannot be more than 1,000 kilogram. So now you decide, this is fixed. Now how big is the satellite is fixed, how much propellant is required is fixed. Now you try to accommodate all these things that for a satellite to work, there are a number of systems required. Now you try to accommodate all the systems. Then you find out how much you can reserve for the payloads, mass and power, how much you can reserve for payload. Now the satellite is conceived. Now we have to also find out what are all the sensors that are required for reaching moon. So from Earth to reach moon, there are some number of sensors required. You identify what are the sensors. And also after reaching moon, to do the landing, you require some special sensors. You identify what are the sensors. Now all these sensors need to be not only developed, but also need to be characterized. Because the success or failure of a mission depends on many things. One of the main thing is how good is your sensor, how good you are able to get the required information about the trajectory, landing area, velocity, hazards, like that. Many things you need to know. These are all done by sensors. How good is your sensor is a very, very important aspect of a successful mission. So you have to identify the sensors, develop them, and start characterizing them so that you can you know how the sensor is going to perform. Then you also identify what are all the simulations that need to be done. Both you can do simulations in software, hardware, mix of software and hardware. One of the challenge in missions like going to moon is that we have to characterize the sensor, because the sensor's characterization is important. The most difficult part of a mission to moon is that it is not possible to simulate the conditions of the travel and landing. That is how to descend from an orbit to the moon. Exactly simulating them is not possible. To give you a perspective, when the lunar craft, when it is around the moon in an orbit and starting to descend onto the moon surface, it has a velocity of about 1.6 kilometer per second.
Yes.
Now, from that speed, it should come to nearly around 1 meter per second speed to decelerate and land. Now, during this entire range, all your sensors need to work. All equipments need to work. Now, how do you test that your systems will work when it is moving at this speed? Because all our optical sensor are microwave sensors. They are all affected by relative velocity, isn't it? So this is the main challenge of doing missions like lunar missions, that it is not possible to test the sensors and your algorithms in the actual service conditions. So you have to do what is feasible on ground, what maximum you can do on ground. You can use an aircraft or a helicopter or a car or train, or this much only is the maximum. So highest velocity what you can get is with an aircraft. Aircraft at best can go at a speed of about 700-800 kilometers per hour, which is at least 2 orders of magnitude lower than what the sensors are going to experience. This is the major problem. All systems cannot be tested in the service conditions. So how do you come out of this? By doing a large number of simulations in various conditions, so that your model and the sensor performance you will match in these various conditions, and use the model to predict the performance in the actual service conditions. So this is how it is done. So this is a very involved work to characterizing your hardware and software for conditions which can be tested on ground. You validate your mathematical model with this and use that model to do a computer simulation to find out how it will actually perform in the mission. So this is a very long duration activity. This takes a couple of years. In our case, it took us a couple of years. Many people take many years. 1 decade also people have taken to do this kind of simulations. Now, once you do all these things, you realize all the systems, assemble them. You have to go through a set of tests to verify that the hardware will survive the vibration, the temperature excursions, the vacuum environment, all these environment it will survive. To verify that, you have to go through a large number of tests, then take the craft for landing. Now, after doing all these things, the most important thing beyond this is the review. That what you have done, it needs to be reviewed by experts who are not actually involved in your work, so that they can give an independent assessment of what has been done, whether it is adequate, because these independent experts have not only knowledge of the subject, but also have knowledge of what has been done by others. Yes. So you go through a series of reviews to identify what you have done, whether it is adequate, if there are any shortcomings or lacuna in what you have done, so that they can get corrected. Go through the test regimens once more and declare that this system is ready for launch. This is how, from concept to realization of the hardware, a large number of steps are involved, and it is quite an involved process.
Okay. So, what was as Chandrayaan-3 was full of so much sophisticated engineered parts. So, what was the most hardest thing or the most challenging thing that was on the spacecraft or the lander or the rover that was quite challenging to the whole team?
As I mentioned, already mentioned in the previous answer, the most difficult part was creating the conditions to test the sensors and gain confidence on the sensors. We have to gain confidence on the sensor. The sensors will perform well. This is the most challenging aspect of, not only for us, anybody who wants to do a mission like a lunar mission or go to Mars and land. This is the most challenging activity. In that, the important challenge is making a model, that is a mathematical model of your sensor, which is physics based. See, you can make a data driven model, you can make a empirical model. These can work only when for the conditions for which you have fed the data and the data is valid. Whereas a physics based model will allow validation at conditions which are different from the service condition, but physics remains the same. So a physics-based model produces exactly the same result at even different service conditions. Its prediction in the actual service conditions are more likely to be correct. So making a physics-based model or a physics-derived model for the sensors was the most challenging aspect of these Chandrayaan missions.
Okay, sir. Sir, as Chandrayaan-3 landed over the moon's south pole, a region which was not explored by anyone else before. So, why is this region so much significant for ISRO or for the study of moon?
There are two main reasons. The poles of moon are important. Both north and south poles are equally important. The north pole of the moon is even more hazardous than the south pole. I will tell you what is the difference subsequently. The reason the interest in the poles of moon is that there are large mountainous terrain which is resulting in some areas in these poles which has never been touched by sunlight. It means there are zones in the north and south pole of moon which are permanently shadowed. They never see the light of the day. It means they never get heated. It means they are always very cold. So there is a big possibility that some important chemicals, minerals can be there in the poles, because Americans have gone to the moon near the equatorial region in the late 60s and 70s, and they found there is actually nothing other than the lunar regolith. There are no material of significant use in the equatorial region of moon. Whereas since the south and north pole of moon have large areas of permanently shadowed regions, which are likely to be at temperatures below -100 degrees centigrade, there is a possibility they may contain, say, liquid or solid. There cannot be any liquid water there. It can be a ice, solid water, or any other chemicals, minerals, which will be of use to humanity. So this is the first reason why there is interest near the poles, because the equatorial region of the moon has already been shown there is not really much of interest to humanity. The second reason is the moon is constantly being bombarded by the micrometeorites and asteroid particles which are there in the space. In Earth, you don't see them much. Once in a while, you will see a small micrometeorite coming like a streak over the sky, because Earth is protected by its atmosphere. So any micrometeorite hitting Earth has a very low probability. Very big micrometeorite comes, or asteroid comes, then only there is a possibility of it reaching the surface of Earth. Atmosphere will ensure, because of the friction and heating, the whatever incoming material will burn out. So it will not reach Earth's surface. Whereas Moon doesn't have a protection like this. Moon is constantly being bombarded by micrometeorites. That is the reason why the surface of the Moon is pockmarked. It is like small craters are there in the entire surface of Moon because of the constant bombarding of the Moon by micrometeorites. Now, what is happening because of this is these areas now do not have the original material of which the Moon is made, because it is being bombarded by something coming out from somewhere else. Some foreign material is coming and hitting. In the process of hitting, it not only takes out the material from Moon's surface, but also deposits its own material on it. So wherever the micrometeorite hits have happened, the material present on the surface of Moon is not Moon's original material. These have been contaminated by the materials that are coming and hitting its surfaces. Whereas the poles being like, it is like if you are having a ball and constantly a stream of particles coming, the poles are the places where they have the least probability to hit. Whereas the equatorial region of the ball is the most probable place where it will come and hit. So the lunar south and north pole are the regions where the probability of finding virgin lunar material, original lunar material, is high. So if you want to study the origin of Moon, when it started, how it was there, you need to study near the poles, so that you can find out what were the original material that Moon was constituted. Because even today there are two theories of how Moon got created. So this is one of the reasons that you can find what is the original material on the Moon surface near the poles. So the permanently shadowed regions, which has a potential for water, ice, and other minerals, and also the possibility of having original Moon material near the poles, are the reason why the South Pole and North Pole are important. North Pole is more difficult to land because it has even a lesser flat area for any landing to happen. Almost completely that North Pole of the Moon is zigzag, very hazardous surface.
So, as you have mentioned that the moon is completely composed of various kinds of ups and downs, mountains, craters, and all. So, I remember that the landing sequence of Chandrayaan-3 and even Chandrayaan-2 was completely autonomous. And how does the lander choose its spot, that where it has to land? What was the sophisticated technology? In a simple words, can you explain them, please? And can you please tell that what you have corrected in Chandrayaan-3's lander, which was not in Chandrayaan-2, means why it failed, and which corrections we did in Chandrayaan-3's Vikram lander and it succeeded in the attempt.
Any landing mission cannot be realized as a first landing mission. Before any landing mission, you require a remote sensing mission. Sometimes what we do, the landing mission itself, before landing, it will do the remote sensing. It means it will stay in orbit around the object, take pictures, images of the planet or Moon where you want to land, so that you know where you are going. The first step is to do remote sensing of the planet or Moon. So every lander before landing has done that, or used the data from a previous orbiting mission which has given the pictures. We also did exactly the same thing. During Chandrayaan-2 time, we took the help from the NASA to get pictures of the landing sites as taken by the NASA's lunar missions. So we know how that terrain looks like with a very coarse resolution picture that was available from NASA. Now we try to make a digital elevation map. It is like a three-dimensional map. So the first starting point of landing planning is that you want to make a digital elevation map of the area of interest. Now, after making the digital elevation map, you find within that area that whether there is a surface where sufficiently flat. It will not be completely flat like a airport runway, but reasonably flat area of the size which you require. Now, Chandrayaan-2 was roughly about 5-meter diameter. You can take when it lands, it will be about 5-meter diameter. Now, the landing area was to be chosen something of the order of, say, 250 meter by 250 meters. So if I find a place 250 meter by 250 meter, which is reasonably flat, then we can choose this is the landing site. So from these pictures, first you decide this 250 meter by 2 meter, or in the case of Chandrayaan-3, a 2.5 kilometer by 1 kilometer strip was identified as a place potential for landing. Now, once you have done that, what you do now, this zone, you try to take pictures and try to identify whether there are any craters or rocks which will make your craft to topple. With that, you are trying to make a map of that landing zone, a small area. In Chandrayaan-3 case, 2.5 meter by 1 meter, that much area, 1 kilometer by 2.5 kilometer. It was mapped with craters and boulders as seen by the Chandrayaan-2 camera. Chandrayaan-2, we did it with the NASA's cameras. So this, once you have done, you also have some high resolution camera in the lander itself. Chandrayaan-2 and Chandrayaan-3 both had high resolution cameras. Now, if you take a picture from 100 kilometer, you will get some resolution. Whereas if you are taking a picture at 50 meter or 100 meter, you are going to get more details, high resolution image you will get. That is what is used to identify hazards. This is called lander hazard detection camera. So you had a hazard detection camera. What it did was, from about 1 kilometer onwards, it is continuously taking images, 1 kilometer from the surface height, continuously taking images, and about 100 meters when we are reached, now it is taking a picture and comparing with the map what you have made and trying to identify whether you are landing in the correct place. Then at about 30 meters to 10 meter, in that range, it takes another picture and see whether right below its legs, whether there are any hazard, that is either a crater or a boulder. If there is a hazard, then it tells you have to move left, right, forward or backward. So the craft will be made to move left, right, forward and backward in situ. Because of the camera's image, the lander understands that there is a hazard which is at right below where it is going to land. So I have to move by 5 meters to my left. This is exactly what happened in Chandrayaan-3 also. That the hazard detection camera detected there was a hazard. So the lander moved to the left by about 5 meters. Then confirmed that there is nothing below, we can land. It landed. So almost all the activities done using cameras. Cameras before launch, cameras during the flight, cameras just before the landing.
Yes, sir. Sir, it nearly took 2.5 hours after the Vikram's touchdown into the moon surface and for the Pragyan to actually roll out on the surface. Could you tell us what happens during that gap? And also, why that waiting period was so much important?
See, when the lander is touching down, there are final phase, 2 engines were firing. When any engine fires, it has an exhaust. When the exhaust hits the lunar surface, the dust on the lunar surface goes up, because it is a very fine dust which is there on the surface of moon. So as the lander is about to land, when it is coming closer and closer to the surface, because of the exhaust from the engines of the lander, the dust will be kicked up. So first thing after landing, what you need to do is, once you have confirmed that landing has happened properly, give time for the dust to settle down, because you do not want the dust to come into the moving parts of the rover and onto the cameras and other sensitive surfaces on the rover, and making them not working. So we have to first give time for the dust to settle down. So we have to give some time for dust to settle down. Then the second part is, the rover is kept off inside the lander. To come out, you have to open a ramp of the lander so that the rover can slide on that and come to the surface of. All these activities have to be done. So when inside the lander, the interface between the lander and rover is through some mechanical arrangement. Now, for that to be released and separated, you need to bring them to a temperature which is above 0 degrees. Because at lower temperatures, what is known as cold welding will happen. It is two metallic surfaces. When two surfaces are making contact with pressure, if it is very cold, they will get welded. They will join permanently. It is called a phenomena called cold welding. So you need to avoid this. If you have to release them, what you have to do before you try to release them, you need to first heat them to come too close to room temperature. Then you can fire the current, cut the bolt using a pyro cutter and release it. So this is a second act. With that, we have to heat the bolts which are holding the rover to the lander, so that cold welding does not happen. Third one is, you have to now deploy the rover ramp and switch on the rover, deploy its solar panel. Rover's solar panel needs to be deployed so that when it comes out, it will start generating power. All these activities have to be done before we actually roll out to the rover. That is why it took about 2 to 3 hours.
Okay. So, as we are seeing that India is also gearing up for Gaganyaan mission of sending humans into space. And in the near future, our Prime Minister and ISRO has dreamt of sending humans on the moon by 2047. So, sir, what is the biggest challenge that one could have on the moon to make it habitable and to send astronauts into the space or to land over the moon?
The first biggest challenge is the cost of going to moon. As I told, if you want to land 1 kilo on moon, you require propellant of 5 kilos. Whereas if you want to make man live continuously on moon, you should also make provision for the coming back from moon. It means that if 1 kg has to go onto the moon and coming back to Earth, the requirement is of the order of 10 kilos. So to take 1 kilo and part of it to come back, you require 10 kilos to be taken out. That much it is. Cost of the rocket, cost of making such a huge rocket. Now, if I want, our biggest rocket today has a capacity of 4 tons. So it means that to land on moon, you can take less than 1 ton. So that is why Chandrayaan-3 was only 700 kilogram landed on the moon surface. Whereas if you want to land moon with a man and make provision for him to live there and come back, huge amount of, say, several thousand tons of material has to be landed on the moon. So the cost of doing this is today very high. This is a major challenge economically, but this is not a technical challenge. If somebody has infinite resources, yes, all can be done, but this is a challenge. Number 2 is the vacuum and the gravity. Moon doesn't have an atmosphere, so man has to all the time be inside a space suit, or you have to create a bubble inside which you can have oxygen and other constituents of the air, so that man can safely breathe inside. Because man cannot also safely breathe pure oxygen also continuously. Pure oxygen can be breathed only for a short duration, cannot be done for a very long duration. So what you require is huge bubbles or huge habitats which are pressurized. So it means, so again, mass, material, if you want to think of carrying all this from Earth, it is going to be very, very difficult. You need to find a way of generating these things on the moon surface. That if you are able to find a way of generating oxygen and nitrogen on the moon surface, remaining on moon will become that much easier. So you should find a way of generating oxygen and nitrogen on moon. This is the second challenge. The third challenge is energy. That is, for anything to be make any place to be made habitable for a human being, you require energy. That is heating and food. All these things, for everything you require energy. That is power. You require huge amount of power to for the human being to survive on the lunar surface. So along with oxygen, you also should be able to generate huge amount of power. Solar panels, even on Earth, you are finding it difficult, because even today, the contribution of the solar power to the national power generation capacity is less than 2%. Out of the total country's electricity need, less than 2% is generated by solar panels. So you cannot, it is that difficult to make with solar panels. So you need another source of power generation. The most probable source that is being talked of is nuclear power generation. So, but again, a nuclear reactor building on moon surface, how heavy it is going to be, you can imagine. So these are all the challenges. One final challenge, which is not so trivial, is the gravity. Because even though moon has a gravity, it is 1/6 of what is on Earth. So all humans can adaptively learn to live in a lower gravity. But the tools and machines what we have developed on Earth, all of them may not work as good as they work on Earth, because all design has been made for this 1G gravity condition on Earth. So many of the systems, equipments that are made on Earth, if they have to work in zero gravity when they are in orbit, or on the lunar surface where it is 1/6 gravity, they have to be adapted, they have to be modified. These are all the challenges in continuous sustained presence in the lunar surface.
As you have spent your life studying the universe through equations and engineering, has that shaped your sense of specialty, or how do you personally define it?
See, as I told, my study discipline was physics.
Mhm.
And the space activity is a multidisciplinary activity. It involves various disciplines of science and engineering. So my training in physics has allowed me to understand the physical principle of how things work, how things are made. So that is what is the my advantage as being a physics student, is that I'm able to understand the physical principle of how things work. And as also physics and mathematics are very tightly related. At higher level physics is nothing but mathematics, and higher level mathematics is nothing but physics. So mathematics and physics are the two subjects which mathematics allows you to analyze, compute, calculate things which can be modeled and which can be predicted. Physics gives you the ability to understand things, how they work. So these are the two things that are required for any engineering or technological discipline to become successful. You will be a expert in, say, for example, one of you is biotechnology, one of you is studying it. But biotechnology, to study also, you should understand some chemistry and some physics. Without the understanding of physics, chemistry, and mathematics, biotechnology also, it is not possible to excel in biotechnology. So basis of everything remains these three subjects: mathematics, physics, and chemistry. All life sciences, even today arts, people require machine learning and artificial intelligence, which is nothing but mathematics. So what is required is all engineering discipline, every principle, every theorem is required, but the physical basis and the analytical mind of the state of mind, if you are able to analyze things analytically, they are allowing you to excel in any domain. So these are the two things: the physics, and every problem should not be seen as only a mathematical jugglery, or as a problem of heating, cooling, like that. We have to think what is the physics behind that, and how do you convert the physical problem into a analytical problem and analyze it, because physical problem can be understood, but to analyze you require mathematics. So that is how the skills need to get developed.
Okay. So 15th August is approaching, and following that 23 August is also approaching, and marking the anniversary of Chandrayaan-3's landing on the moon. So sir, what message you want to convey to the youth of this country that about achieving their dreams like ISRO, and struggling with the hurdles and succeeding over them? And what kind of message you want to give to the youths of this country?
Message is that believe in yourself. Nothing is impossible. This is what I would like everybody to, not only to the youth, even not so young people also, should start believing that everything is possible. Only we have to aspire for it, and you have to work for it. When you start work, you can aspire for many things, but when you start working towards that, you will understand how to do it. Or if something is not doable in the way we have thought, we will try to find out another way of doing it. I should quote here our founder, director, and the father of satellite technology in India, Professor R Rao. He is famously attributed to these two quotes, that if someone can do it, we can do it better.
Yes.
If no one has done it, you have to necessarily do it. So these are the two principles which will make us achieve every dream. We can dream many things. The dream is important. First, dream has to come. But dream alone is not sufficient. Dream has to be made reality by methodical hard work. So when you do methodical hard work, you will also find some of your dream may not be realizable in the way you thought you can do it. So you will find, when you work towards that, you will find an alternate way of doing it. So this is the message I would say, that dream and work methodically towards your dream.
Okay. Yes. So finally, we are coming towards the end of this discussion. We want a small message for our team. As we at BHU, we have made a small team for science communication, and here we simplify the quite a complex and sophisticated language of science into the simple words in a simple language too. We communicate it in Bengali, in Telugu, in Hindi, in English, to the audience, to the students, or to the common people here at BHU and around us in the schools nearby. Sir, I want you to give a small message for our team.
First, let me congratulate and compliment the Achintya team of BHU for taking up this onerous task of science communication. It is not only difficult, but it is essential. Science and the mentality of science. If somebody cultivates the mentality of scientific inquiry, many problems of not only our country, the entire humanity can get resolved. If every problem, if it is approached scientifically, not only you will achieve solution, we will also identify what are unimportant, unproductive things which lead to conflict between people. So one best way of conflict resolution is developing scientific communication. And since Achintya is doing this scientific communication, I must congratulate and compliment all of you, particularly doing in Indian vernacular languages, which is most important because almost all technical and scientific literature in the world is in English, most of it. Though there are some literature available in some other languages like German and Japanese, and of late in Russian and Chinese also. Most publicly available technical and scientific literature is in English. And today also we are talking only in English. But more than 90% of this country's population do not understand English, or any single language is not understood by a large section of the population. So it is essential that the science as well as the importance of science is taken to the people in the language they understand. So for India, our national languages, which are all our official languages are considered as national languages by our Indian Constitution, and there are 2 official languages here. So irrespective of what is the language we speak and we study our subjects, if we want to convey the essence of science to the public, it has to be done in their respective mother tongues. That is the best way to communicate the information. So the Achintya team, which is mainly working initially in science communication in Hindi and now in all other Indian languages also, is doing an outstanding service. I wish that you continue this service and also this attitude towards making the information reach in the medium which is understandable by the target audience. That is more important. I can speak in English. I cannot speak this fluently in my own mother tongue. That itself is a problem because all my education and higher education and communication after coming to work has become in English. That is the reason. But this needs to get changed. If we need to broad base our knowledge in our country, it is essential that this science and engineering education happens in the respective mother tongue, so that we become a completely scientific community. That is what is being told as the India's past. Some ancient literatures tell that India as a whole nation was a very, very advanced scientific community. Probably at that time, people were learning things in their native languages. Maybe because we have abandoned the native languages and chosen to learn in English, probably we are now finding that the literacy is only about 70%. That also, after so many years of effort, it has reached about 70-75%. So literacy alone is not sufficient. Scientific literacy is what is required, which is best achieved through science communication, through vernacular. And for doing that, congratulations to the Achintya team. And BHU being a historical university of more than 100 years of heritage, and I'm very, very happy to be part of this program with you young guys. And I compliment and also wish you well for all your future endeavors. Thank you.
So in this meeting, we got to discuss the various things, including the various exciting and interesting topics, which you might have seen on the media channels or various different channels about ISRO on YouTube channels or Instagram pages. But today we discussed about the backstories and what happened behind the scenes with the scientists who were watching the real-time data coming up from the moon. How was the Vikram got landed, and how the rover initiated its journey on the moon. And we discussed the mechanism behind those engineering technologies. And we discussed about the hard work, the perseverance, and the passionate culture of ISRO that works behind those missions. So we thank Shri Sankaran sir for joining with us and blessing us with his very inspiring words. And thank you from the whole fraternity of BHU students of the BHU and our whole team. Thank you so much.
Thank you, sir.
Thank you.